We move to the last talk of the session. The speaker is Marco Cuyubamba from Oldenburg University, who will talk about stability of asymptotically de Sitter and antidS black holes in four-dimensional regularized Einstein-Gauss-Bonnet theory. Marco, are you here?
Yes, I'm here. Can you hear me? Can you hear me?
Yeah.
Okay, perfect. Let me share my screen. A minute. Okay. Okay.
Yeah.
Okay. Thank you. Well, my name is Marco Cuyubamba. I will present my recent work, which is stability of asymptotically de Sitter and anti-de Sitter black hole in four-dimensional regularized Einstein-Gauss-Bonnet theory. Recently in this year, at the beginning of this year, was proposed a new theory of gravity, a modified theory of gravity in four dimensions. This is strange because initially this is strange because there is a theorem which states that the unique four-dimensional theory of gravity with 2 degrees of freedoms and differential dynamical equation in second order is the Einstein equation. Is the unique. But this theory proposed at the beginning of this year seems that bypass this theorem. And we are focused to study black hole perturbation in this theory. Well, I would like to explain first what is the Lovelock gravity. The Lovelock gravity is considered as an extension of the Einstein gravity for higher dimensions. In this expression 1, you can see the density Lagrangian, which depends of the cosmological constant, lambda, and have these terms. Okay, have these terms. This alpha parameter are arbitrary parameter, and this Lm corresponds to the Lovelock term. How it works? For example, when you have four-dimension space-time, in the summation of this expression 1, you consider just up to n equal 2. In this case, the action corresponds to the Einstein-Hilbert action. L0 is equal to 1, L1 is equal to R, which is the scalar curvature. And this is the Einstein-Hilbert action. But this is in 4 dimensions. But when you consider higher dimensions, in this case, dimension 5 or dimension 6, you need to consider a second order in curvature. In this case, you need to add L2, which is well known as a Gauss-Bonnet term. This Gauss-Bonnet term is interesting and important because appears in the heterotic string theory naturally. Okay, in some research consider this term as a quantum correction in order to explain the connection between general relativity and quantum mechanics. Okay. In higher dimensions, in this case 5 and 6 dimensions, you need to add this term, and the action is modified, and depends on this parameter, this alpha 2, which is a coupling parameter. This is an arbitrary parameter of the theory. Okay. But it works in higher dimensions. If you consider alpha 2 in d equal 1 in 4 dimensions, L2 is equal to 0. L2 is a topological invariant in 4 dimensions. And you come back to the Einstein theory. Okay. Well, at the beginning of this year, Glavan and Lin proposed a new theory in 4 dimensions. What did they do? They consider a higher dimensional theory, and then goes a limit to d equal to 5, makes a dimensional regularizations, and consider the expression 3. This alpha 2, remember that is the coupling parameter of the action. Yeah, is a coupling parameter, and they rescale the coupling parameter in this form. When they begins in the higher dimension and goes, take the limit d equal to 4, they obtain a non-vanishing term. In this case, this Gauss-Bonnet test is not vanishing in d equal 4. And this is interesting because they propose a theory which bypass the Lovelock theory, which states that Einstein's theory, they are unique 4-dimensional with 2 degrees of freedom. Well, we're interested to study black hole solution and linear perturbation. In this case, if you take in the variation of the action, you can obtain an Einstein-like equation. It's not a G, for example, G mu nu is not an Einstein tensor because this tensor is added, is an Einstein tensor plus other terms which depend of the Gauss-Bonnet parameter. If you consider the vacuum solutions, it's possible to obtain analytical solutions. The line elements it's similar to the Schwarzschild solution, but it's not Schwarzschild because Schwarzschild is a solution in the Einstein theory. In this case, after it has this form and depends of alpha 2, the parameter of the Gauss-Bonnet parameter, and the lambda, which is the cosmological constant. M corresponds to the mass of the black hole, and it's always possible to express the mass of the black hole in terms of the other parameters. And you can see that we have a theory of 2 parameters. In this case, we have the Gauss-Bonnet, the coupling parameter alpha, and the cosmological constant, which is lambda. Okay, we're interested to study linear perturbations. Okay, what is linear perturbation? Just adding a perturbation which verify these conditions. The equation 5, equation 6. Yeah, and it's always possible after perturb the background, after perturb the metric. It's always possible to express this perturbation in this form, the expression 7. What is this? It's a differential well-like equation. It has an equation of waves. And in this case, V, it corresponds to effective potential. Psi corresponds to the perturbations. In this case, psi is a linear combination of spherical harmonics on some other function which depend of the radial coordinates. For the case of gravitational perturbations, you can study 2 channels, independent channel. You can study independently these 2 channels, which is the vector and scalar perturbations. In 4 dimensions, you have only have a vector and scalar. If you study higher dimensions, you have vector, scalar, and tensorial perturbations. But in this case, we have vector and scalar. And the effective potential is well known in the equation 8 and 9. I don't shows the function T and R because it has a large form, but this function is a function of R, which R is the radial parameter, okay? And depends of the other parameter, the coupling parameter and the Gauss-Bonnet, the cosmological constant, okay? And depends of this parameter L. This is important because this parameter corresponds to the multiple number of the spherical harmonics, okay, and goes from 2 to infinity for the case of gravitational perturbations. We use a technique in order to study the stability of these gravitational perturbations. We use a technique which is a characteristic integrations. We can express the equation 7 in terms of the Lycon coordinates, and you can express, you can obtain this equation 10. It's possible to discretize this expression in this form. The idea of the method is the following. You consider the blue point, you consider as an initial perturbation, but basically you have a black hole. You perturb a black hole with an initial perturbation, which could be a Gaussian perturbation, for example. It's a it does not depend on the initial perturbation. You consider any initial perturbation in the blue points. And the idea is with this expression psi n, you can to obtain the value of the perturbation in any point of the grid. Okay, with this method. When you go, the diagonal corresponds to the evolution of the perturbation. Okay, the diagonal. The idea of this is the following. When you obtain this, all of these points in the diagonal, you are obtaining a picture, the perturbation, and the other axis is the time evolution. Yeah, is the time. And you have a temporal profile, how the perturbation evolved after an initial perturbation. And you have a graphic similar to this. This first part corresponds to the initial perturbation, it depends on the initial perturbation, but then stabilize in this form. This form depends on two values. Depends on the one frequency, which is complex frequency. The real part of this complex frequency corresponds to the oscillation of the perturbation, and the imaginary part corresponds to the decay rate of the perturbations. This is well known as the quasi-normal modes. Okay. For late times, the perturbation generically has this form. Okay, goes to zero. It's a typical temporal profile of a perturbation of black holes. But what's happened? For certain values of the parameters, in this case alpha and the cosmological constant, the black hole is not stabilized. In this case, how we can study the stability of black hole? The red corresponds as an unstable black hole, and the green corresponds to threshold instability, and magenta corresponds and the unstable black hole. And we are interested to obtain this limit, the threshold of instability for any value of the parameter. Okay. Of course, there are some parameters. There are no oscillations. Only appears the domination of the quasi-normal, the imaginary part of the quasi-normal modes. Okay, but the idea is similar. And you obtain this parametric ratio. And this is important to see the following. In the horizontal axis, you have the Gauss-Bonnet term, the alpha coupling, parameter alpha, and in the vertical, you have RH over RC. RH is the radius of the black hole, in RC corresponds to the cosmological horizon. In this case, it's for the Sitter spacetime. Okay. The bottom corresponds to the asymptotically flat. In the top corresponds to the extremal value of the black hole. Okay, it's important to remember that the perturbation depends of the spherical harmonics, and the spherical harmonic depends of the parameter L. The perturbation is a linear combination of all the spherical harmonics and depend on L. Okay, generally, L equal infinity correspond to the largest region of instability. This blue region corresponds to unstable black holes, and the white corresponds stable. And this line corresponds to threshold instability. Generally, in Einstein gravity, you can observe that L equal infinity corresponds to the largest region of instability. But what happened in this case? In this case, you can see the following. You can see that the L equal to the lowest value of L has is relevant for a larger black hole. Okay, there is these two graphics must be overlapped. Okay, and you can obtain this when you consider this alpha coupling. Okay, this parametric region instability for the Sitter spacetime. For the case of antidS theta, the L equal to is always inside the region of L equal infinity. In this case, L equal infinity corresponds to the most unstable region of instability. This black corresponds to, there are no solution of black hole in this black region, okay? In antidS theta spacetime we can express the value of alpha for stability. For alpha 2 higher than this expression, mu squared over 2, and lower than this expression, okay, the black hole for antidS theta spacetime is always stable. This value is determined, A, B, and C are determined here. And mu is the fraction between R plus, which is the radius horizon, and R is the antidS theta radius. In these two pictures, okay, the parametric region of black hole is determined. It is interesting in this case because this L equal infinity has a vertical asymptote. Okay, I cannot show you here, but it has a vertical asymptote, and this means that there exists a minimal value of alpha, which in the black hole is unstable. Okay. We have studied also the isospectrality. What is isospectrality? Is the following. For gravitational perturbation, you have two independent channels, the scalar and the vector perturbations. And you can see that in Einstein gravity and the theta Einstein gravity, you can see that because the normal modes are the same for scalar and vector type perturbation are the same. The frequency oscillation and the decay rate are the same. But what happened when you consider in this in Einstein for the regularized Einstein-Gauss-Bonnet black hole? The isospectrality is broken. Okay, maybe in this table I can show the following. Alpha 2 equals 0 correspond to Einstein gravity. And you can see that first correspond to the quasi-normal mode of the vector type perturbation, and the second correspond to the quasi-normal modes of the scalar type perturbations. And you can see what are the same. And it's happening for any value of the cosmological constant. Yeah. But when you add the Gauss-Bonnet term, the isospectrality is broken. The quasi-normal modes are not the same for the vector and scalar perturbations. Well, it is my work. Just for my conclusion will be that the following: we obtain a full parametric region of stability in 4D Einstein-Gauss-Bonnet gravity, de Sitter and de Sitter black hole for any value of the cosmological constant alpha coupling parameter. We cannot find indication of lambda instability is the instability of L equal 2. This is the name of this instability, L equal 2, and the instability of L equal infinity is the eikonal instability. Is the name of this instability. In antidS theta, there are not appears indications of land instability because it's inside to the eikonal instability. We observed finally we can observe that isospectrality is broken for this new theory. Thank you.
Okay, thank you, Marco, for a really nice presentation. Okay, now let's move to the discussion part again. If someone has a question, please.
I have a question.
Okay.
So could you please turn to the slide 4, the beginning, slide 4.
Here?
No, I think
here.
it was equation 4. Yeah, here. So as you can see, you have a radial function fr, and it's seen that when R tends to infinity, then this part does not tend to 1, right? So we will not have a flat spacetime at asymptotical infinity, even in the absence of cosmological, even in the absence of cosmological part. So,
exactly. Yeah. When you go to R into infinity, you have a dependence of the cosmological constant. I study two different asymptoticals, the sitter and anti-the sitter. Okay, when you go to infinity, this goes to 0, and you can obtain the anti-the sitter or the sitter solution.
Okay.
Thank you. Okay, thank you.
Okay, next question.
Yes, I have
Camilo?
a question. Can you hear me?
Yeah, you can.
Okay. Yeah, I'm just curious about if you also consider maybe rotation. So I'm curious about what happens if we introduce rotation in this new theory with alpha different from 0.
Yes, there are
the Kursky equation, kind of, you know.
Yes, it's interesting. I don't study the rotational black hole solutions. There are some people that are studying the rotation, and maybe appears a region of stability in this rotation. I don't remember the paper exactly, but I remember that appears a region of stability for this rotation also.
Okay, thank you.
Thank you.
Okay, can I ask the question? Can you open the page number 8, please? Here it was like an evolution of the perturbation we had here. If you look at this second wave is this inclined decreasing region, here it's like a ring down, yeah, am I right?
Yes, exactly, yeah.
Yeah, here the black hole is getting stabilized, but when we reach to the tail, here it's becoming immediately unstable, yeah, am I right? In this one, in the above one, upper one.
Yes. Yes, it's unstable. Yes.
It like this, black hole is becoming, at the beginning it was becoming stable, it's stabilizing, but at some stage this process is stopped and it became some kind of unstable, right? It is so?
Yes, really these tails, yes, which occurs for large time, appears for what? If the tail increases, it means that the perturbations don't verify this the equation 6, for example. The perturbation has an order of magnitude similar to the metric.
Oh yeah, it's dominating, yeah.
Is dominated. There is some time that the perturbation is dominated with respect to the metric, and this is an instability in linear perturbations. Which the perturbation is unstable in linear, of course, will be unstable for higher order of perturbations. This is the idea of this.
Okay, thank you.